Welcome everyone. So first, let us start with a basic question. So what do we do in physics? Bye. Now is it better? Am I audible? Now it's not working. I don't know. Hello. Does it work now? Okay. Okay. So I'm going to start with a basic question. So what do we do in physics? Since it is the school is mainly focused on physics. So what do we do in physics? Hello. Hello.
Is it audible at the end?
Volume.
সাদমান ভাইটা কিভাবে কাজ করবে? সাদমান ভাইটা কিভাবে কাজ করবে? না, মাইক্রোফোন আলাদা ছিল। মাইক্রোফোন আলাদা দুইটা। হ্যাঁ, ওইটা আচ্ছা ওইটা ইউজ করে দেখি।
Hello. Is it okay now? It is better? Okay. আরেকটু ইনক্রিজ করতে। Hello. Okay. 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 So the question is, what do we do in physics? We basically do measurement, right? And so then the next question is, what do we expect the physical theory to satisfy? Or is it, if I take some transformation or do the experiment in a different setup, then what will be the outcome? So these are the questions that we are actually interested. And to do this, we need mathematics. So, and basically we are going to start doing mathematics from a basic starting point, which is the set. And to understand the set properly, we need functions. And most of the observables in physics are actually functions from a set to another set. So let us start with the definition of set. So what is a set? A set is any unordered collection of objects. So this is actually the set. Now, what are the examples of set? Let's say examples A, 1, 2, and 3. This is a set. Also, another example can be say B equals to alpha, beta, and gamma. Now, what are the objects in a set? So the objects are like 1 is an object in A. And can a set be an object? It can be. So I can consider a new set C, A, and B. So A is a set and also an object. But A is an object of the set C. Not necessarily, it can be anything. Yeah. So I define the set to be a set is any ordered collection of objects. The objects can be anything. Yeah. Okay, now to study the set, we want to consider relation between sets. So what is a relation? So to define a relation, we need two sets. Let us consider A and B. These two are sets. Then the relation is a subset of the Cartesian product of A cross B. But function is a more structured relation. So a function is a relation from a set X to a set Y that assigns each element of X exactly one element of Y. So this is a function. Now let us see an example of a function. So let us consider, and also before moving on, let us consider different types of sets. So we also have sets, the set of natural numbers. The set of rational numbers Q, and finally the set of real numbers, and that is R. We are mostly interested in this set, the set of real numbers. Now to define a function, let us consider the first basic function from the set of real numbers to the set of real numbers, and that is example of the function. So let f is a function from the set of real numbers to the set of real numbers, and it is defined by f of x equals to x. So what does this function do? It gives the same value for every x, right? So this is an example of a function. And now if I take the pair of numbers, like, so for every x corresponding the function value f of x, and if we collect all these natural numbers, all these pairs such that x belongs to R, then this is going to give us a graph of the function, right? And how do we see it? So if I have so I'm considering in this direction, this is x, and in this direction, this is f of x. Then the graph of this function is basically this. So now, okay, so we can have different types of function, even very exotic type of function. That function may not have a algebraic expression. Say we can have a function like f of x equals to the absolute value of x. So this is also a function from the set of real numbers to the set of real numbers, right? And this is a piecewise function. And this function is defined by x if x is greater or equal to 0, and minus x if x is less than 0. Another example of a function is f of x equals to, let's say, 1 if x belongs to the set of rational numbers, and 0 if x belongs to not belong to the set of rational numbers. So there is no algebraic expression for this function f of x, but it's still a function, right? Okay. So now we are going to consider the continuity of a function. So why we need continuity of a function? So these are the questions that we are going to explore in this preschool lectures. So why do we need structures? Like, why do we need continuous functions? Why do we need differentiable functions? Because most of the times when we do physics, we consider the differentiable functions. Almost every observable in physics are differentiable functions, right? We have momentum, and if we take the derivative of the momentum with respect to the time, we get the force. Hence, momentum has to be a differentiable function. We have Lagrangian, and if we take the equation of motion, it is also a differentiable function. So Lagrangian is also a differentiable function. So we are basically interested in differentiable functions, but not every functions are differentiable functions. Like if we consider the function f of x equals to square root of x, is this function differentiable? Yes, it is not. The function is not differentiable at the point 0, right? Because if I take the derivative of this function, then we get f prime of x, and that is 2 square root of x. Now, if you set x equal to 0, then the whole thing blows up, and hence this function is not differentiable. But this function is not differentiable at 0. So basically, we are gonna put structure on functions so that we can get differentiable functions. Like when you will have classes on differential geometry, or probably cosmology and GR, then you need differentiable structure. Okay, so what is a continuous function? How do we define a continuous function? And what do we mean by when we say a function is continuous? How about the function value? Okay, so the limiting value and the function value has to be the same at the point where we are considering the function to be continuous. So let's say we are going to consider the previous example of the absolute value function, and that function is what? F of x. So we're going to consider this function. So is this function continuous at the point 0? So the graph of this function is this is the graph of this function. So is this function continuous at the point 0? It is continuous, right? Because the limit when x goes to 0, absolute value of x, this is equal to 0. And also the function value, sorry, absolute value of 0 equals to 0 from the definition, because it gives you x if x is greater or equal to 0. Hence, the function value is 0 and the limiting value is also 0. So the definition of the continuous function that we always use is a function if is continuous at the point a if limit x goes to a f of x equals to f of x. So this is the definition of a continuous function, right? But we also know another definition of a continuous function, which actually the mathematicians use. And that definition says, for all epsilon greater than 0, there exists a delta greater than 0. So this symbol stands for all, and this symbol stands for there exists. So for all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of a is less than epsilon for all x in the domain with x minus a is less than delta. But what do we mean actually by this definition? So to understand this, let us consider the set of real line and let a is this point. Now, what does this x minus a absolute value of delta means? Or why I'm considering this x in the domain? So it gives us that if delta is a very small positive number, then I will have something like this. So this expression x minus a is less than delta is actually a set. And what is that? That is x belongs to the set of real numbers, because we are considering the functions from the set of real numbers to the set of real numbers. Hence, x belongs to R such that x minus a is less than delta. So this is the set that we are considering. And so now what we can see is, let us just try to picture the whole definition. Then say I have a function from this thing or set to this set. So this is the function f. Although we are still considering the set of real numbers, but let us consider a different set than the set of real numbers. Okay, so the definition says for every epsilon greater than 0, and f of x minus f of a is less than epsilon. So the f of x, so if we consider the set f of x, and if this is my domain and this is my codomain, then this set f of x for all the values of x in the domain, it will be a set of codomain, subset of codomain, or the domain. Subset of codomain, right? So that means this f of x will be something like this. Right? In the codomain. So since it is in the codomain, and from the expression we see this is something like an open interval thing, right? If we consider it in the set of real numbers, right? So in the higher dimension, it may be something like a circle or a sphere without the boundary. Although we did not define what a boundary of a set is, but still let us just intuitively think about it. So this is just a open interval type of thing. Then now, if I consider for a specific epsilon, let's say this is the epsilon, then the definition said there exists a delta. That means if I choose any epsilon in the codomain, then I will definitely have a delta in the domain. So that means I will have a delta in the domain, and this whole thing maps here to there. And from the definition, it said for every epsilon, this is true. Hence, if I change the epsilon and take another open set, then I will have a different delta in the domain set. So this is the idea of continuous function. So for every epsilon greater than 0 in the codomain, there will always exist a delta in the domain. And this gives you the idea of continuous function. And this is always true for a continuous function. Okay, so why do we need such an abstract definition? Because what we are doing, like these definitions, we actually do this in calculus. But when we define it in the context of topology, we are going to set this definition as a definition, and we'll start everything from there. Okay, so now, so this absolute value function, we can define a norm using this function. So norm using the absolute value function. So norm has certain properties, but to define norm, first we need a vector space. But yeah. Okay, so before starting the definition of vector space, let us just consider the norm is something like a distance on the set. So if you consider the set of real number again, then let's say this is the point A and this is the point B. The norm gives you A minus B is the distance between these 2 points. Okay, so also we know the set of pairs of, like, if we consider the set, this set R2 Euclidean two-dimensional Euclidean space. So we know this is a vector space, right? And we know it from probably from school. And also any elements in this set R2, if V is a vector in this set R2, then I can write V like V1 I hat plus V2 J hat. And what is the norm of this vector V? The absolute value of V. This is equal to square root of V1 square plus V2 square. Now, but we also know another operation in this vector space R2, which is known as the scalar product or dot product. And that is also, the product is known by inner product is given by V vector dot V vector. And this is equal to, again, V1 square plus V2 square. Right? That means we can define the norm using the inner product. Right? So to introduce the inner product, we need the vector space structure on a set. A set is barely a set. There is no structure on a set if we don't introduce a structure on a set. So a vector space is a set equipped is a set over the field V is a set over the field F equipped with two binary operation plus and dot, which is known by addition and scalar multiplication. The addition and the scalar multiplication are closed in V, and these operation satisfies the following axioms. So what are the axioms? Yeah. So basically, Kenny and this 4 is for addition, and this 4 is for multiplication, scalar multiplication. So Kenny means commutative. That means if you take two elements in the vector space V, let's say X and Y are the elements of the vector space V, then you can have X plus Y equals to Y plus X. So these X and Y, they are vectors. And associativity. So if you take three elements, X plus Y plus Z equals to X plus Y plus Z. So it doesn't matter which order I'm adding them. Then there is neutral element. So let us just write this. Neutral element, which is basically the zero vector in the vector space V. And if you take any other vector and add it with zero vector, you get the vector back. So this is the neutral element, and this is the additive inverse. And this additive inverse is something like for every X belongs to the vector space V, there exists an additive inverse minus X, such that minus X plus X is equals to the additive identity or the neutral element. Then again, there is an associativity, and this associativity for the scalar multiplication. So if you consider two elements from the field F, let's say alpha and beta belongs to the field F, then and X belongs to the vector space V, then alpha beta X vector is equals to, so alpha beta X vector. So we need to understand one thing here. This dot and this dot, they are not similar. This dot, it is the multiplication. This is the scalar multiplication. You are multiplying a field element or scalar with a vector, and but this dot, it is in the field. So you are multiplying two field elements or two scalars. Then we have distributive law, and this distributive law is something like if you have lambda belongs to F and X comma Y belongs to the vector space V, then lambda times X plus Y equals to lambda X plus lambda Y. Yeah. This one? I mean, which one you are considering? This one? Here? This one is also the scalar multiplication, because if you take the multiplication here, beta dot X, then it gives you another vector, maybe some Y vector. Then you are multiplying this alpha with that vector Y. So this is this dot and this dot, they are same. But this dot and this dot, they're not set. Also, this dot and this dot, they are not set. Yeah. Because you are multiplying two field element, and then like if you multiply 1 times 2, then you get 2. But if you multiply 2 with a vector, let's say v, then you get 2v. Right? So let's say you have a field element 2, another field element 3, then if you take the multiplication, you get 6. But if you have if you multiply 2 into a vector v, then you get what? 2v, right? So you see there is a difference in the multiplication. Okay, so then another distributive law, and this is let's say lambda and gamma belongs to this field, and x belongs to the set v, then lambda plus gamma times x equals to lambda x plus gamma x. And finally, we have the unit of multiplication. So there exists a 1 belongs to the field such that for all x belongs to the V vector space, 1 dot x equals to x vector. So the set V over the field F with these two operations, addition and scalar multiplication, is a vector space. So now let us consider an example. So say we know the scalars, right? So if I consider real numbers, are they scalars or vectors? Like we define vector in physics by a direction and a magnitude. So if I consider just a number, let's say 2, is it a vector or a scalar? I mean, we can't say unless we consider a specific structure. So let us consider the set of real number over the field of real number. So I'm considering the real number set as a field. Also, I'm considering a structureless real number set. So this real number, there is no structure in it. I mean, so far there is no structure in it, but this real number, it has a structure on it. And what is the structure? It is a field structure. So it is a field. So now, if we equip this set R with the usual addition of real number and the multiplication, then this is going to be a vector space. How? So if you take two real numbers, x and y, and if you define the addition by the usual addition x plus y, and the multiplication xy by xy, then you get something like, so one thing that should be specified here, and that is this element, this x coming from which set? This set or this set? So, okay, so there is a, so let us just put a vector over there. So x is a vector and y is a vector. And I'm defining this addition by simply just simple addition of scalar real numbers. And now let X belongs to this arm, and a vector V belongs to this set. Now X times V, so this is the scalar multiplication. And hence, the set of real numbers over the field of real number, it is a vector space, because these two operation, addition and scalar multiplication, it satisfies all the 8 axioms, and it is also closed. So hence, real number can be thought as a vector space. Okay, so we require the idea of vector space because we consider the inner product and an inner product. So definition, an inner product on a vector space V over the field F is a map and this map is defined by something like this. So there is 2 slots. So definitely I will need the Cartesian product of the vector space V. So this slot will be occupied by from the elements of this set B and this slot from this set B. And this will go into the field. So this map is called the inner product map. And it satisfies the so one conjugate symmetry, what is conjugate symmetry? This is just if you have a vector x and y, the inner product, if you interchange their order like y, x, then you need to put a bar on over the inner product. And second is linearity. In the first plot, argument so ax plus by z. So these a and b, they are basically scalars, and this x and y, they are vectors. Z is also a vector. So this is equal to a x vector plus x z plus b y z. But it is not linear in the second slot or second argument. It is only linear in the first argument. And finally, we have positive definiteness. And positive definiteness is something like x is greater or equal 0. So if you take the inner product of a vector with itself, it will always be greater or equal to 0. And when it is equal to 0, if the vector is equal to 0. So x equal to 0 if and only if x equal to 0. But the inner product is a very strong structure. Why? Because to define inner product, you need vector space, right? Without a vector space structure, you cannot define inner product. But we can generalize this idea of inner product to any arbitrary set. And that gives us the idea of metric. So a metric space is an ordered pair m comma t, where m is a set and d is a metric on m a function so d is a function m cross m to the set of real numbers. So satisfying the following examples. So the first one is D is DL valued, finite and non-negative. So D cannot be infinite. Like if you take something like D of x comma y, it cannot give you something like infinite. So D is real valued, finite and non-negative. D of x comma y equal to 0 if and only if x equal to 1. Then it is symmetric. The metric has to be symmetric. So D of x comma y equals to D of y comma x. So one thing I should mention here is these x and y, they are the elements of the set. So x comma y, they belongs to the set M. And finally, the metric has to satisfy the triangle inequality. And the triangle inequality is D of x comma y is less or equal D of x comma z plus D of z comma y. So if a function D satisfies all these axioms, then we say the function D is a metric on the set M. Okay. So it gives us a structure or something which does not require the vector space structure on the set M. You can define a metric on any arbitrary set. Okay, so now one can always define a metric using a norm. Like you can define a metric dx comma y by just x minus 4. Can you give me an example of a metric using this norm, which is known to everyone, maybe on the set of real number? Can I define a metric on the set of real number using the norm? Absolute value, right? So d of x comma y equals to the difference between the 2 points x comma y. You can show this function d satisfies these 4 axioms. Hence, this d is a metric on the set of real numbers. Okay, so next we are going to start topology. But before that, if you have any questions. Yeah.
The thing is, okay, so I repeat, why is the inner product defined so? In case of other definitions, they make sense physically. But the thing is, you define the inner product that they will satisfy conjugate symmetry.
Yeah.
Linearity in the first argument.
Yeah.
So what is actually the problem of symmetry or linearity in the second argument? So what is the reason why we have defined it?
Well, we can define a vector space over the set of real numbers, and we can also define a vector space over the set of complex numbers. So when we define an inner product, we prefer the linearity in the first lot because it gives you a, I mean, you can define the norm using that inner product if you use that definition of linearity in the first lot, and also like the conjugate symmetry, because in complex number you have something like conjugate of a complex number. So, and the norm of a complex number is what? Say you have a complex number C, then the norm of C is the conjugate of C times the complex number C, and square root of that thing, right? So hence we require. Okay.
Would your reason be valid if we took linearity in the second argument?
Yeah, you can consider that. I mean, you can consider either in the first slot or in the second slot, but not in the yeah.
What is the meaning of conjugate in the context of an arbitrary field?
I mean, conjugate in the arbitrary field, there is no. I mean,
the product has to satisfy conjugate symmetry. So
yeah.
What does the bar above y, comma x?
These two bars, like it's not good.
Conjugate symmetry. Yeah.
Yeah, conjugate symmetry, but which bar?
Bar on the right hand side.
Okay. Yeah. Yeah. Thank you. Okay, so you are considering. Sorry. So you are considering this bar?
Yeah.
Okay. So because you can define the vector space over the field of complex number.
Okay. So.
Or you can define the vector space over the set. Yeah.
So the var is basically depends on the field we're considering.
Yeah. And we basically, in quantum mechanics, we consider the vector space over the field of complex number.
Right.
Yeah.
So when we define inner product, the ground field of the vector space is a subfield of the field of complex numbers. So that's why that conjugate makes sense. So in general for any arbitrary field, there's a notion of conjugate. So
okay.
Sir, I have a question.
Yeah.
Sir, if we define the inner product on a vector space that is not complex, then is it strictly necessary that we need to have that symmetry?
No, because if your vector space is over the set of real numbers, then this conjugate symmetry is just symmetry, right? Because if you take the conjugate of the complex number, it gives you just, conjugate of the real number is just the real number. And we know the inner product is basically gives you a element in the field.
But what if we have a weird vector field that doesn't follow the rules of the real space?
No, I mean, you can have a vector space that is not related to real numbers or complex number, but you need to have the field over the set of complex number or the set of real numbers. I mean, you have the field of complex number, you can take the subfield of the complex number, as often said. So the real number is a subfield of the complex number. Also, the rational number set is a subfield of the complex numbers.
So in the definition of set, you mentioned ordered object.
Unordered object.
Unordered object.
Yeah.
But you didn't mention unique. Is it possible to non-unique object be a member of set?
I mean, so
First line.
Yeah. So this is an example of set.
Yes.
And this is also another set, right?
Yes.
But are they equal or not?
Equal.
Equal. How do you know?
Unordered. But my doubt is it possible 1, 2, 2 in a set?
Oh, that is equivalent to the set 1, 2. Because when you define the set equivalence, we say A is equal to the set B if for all x belongs to A, x belongs to B, and for all x belongs to the set B, it belongs to the set A.
Thank you, I understand this. But my question is, duplicate 2 is possible in a set? Is possible?
I mean, it is possible, but they are equivalent. These two sets are equivalent. Any other question? Okay. So now, before starting topology, let us define the idea of, let us consider the idea of interval again. So we consider something like this: x belongs to the set of real numbers such that x minus a is less than delta. So this is a set, right? And this was something like this. This is A, and this is the open interval. Now, we can generalize this definition, and this gives us the idea of epsilon neighborhood. So, given A belongs to the set of real numbers, we are considering the epsilon neighborhood in the set of real numbers. So, A belongs to R, and epsilon greater than 0. So, the epsilon neighborhood epsilon neighborhood is a set given by V epsilon of A equals to X belongs to R such that X minus A absolute value is less than epsilon. Now we can define an open set using this definition. So a open set, as we already know, every open interval is an open set, right? And every closed interval is a closed set. So an open set is set O is a subset of R is open if for all points A belongs to O, there exists an epsilon neighborhood V epsilon of A in O. Like the definition makes sense because if you consider again, let's say you are considering this open interval, say this is 0 and this is 1. Now, if you consider any element in the set, this one, you can always construct a epsilon neighborhood around this point, which is contained in the set 0, 1. Like you can always consider something like this. Even if you consider an element here, you can always consider a very small neighborhood which is contained in the set O. And this is the definition of an open set. Now, this gives us a very interesting theorem, and that theorem is going to help us define the topology on a set. So the theorem open interval, the union of an arbitrary collection of open set is open. The intersection of a finite collection of open set open sets is open. Yeah, I'm gonna explain. Okay, so it says the theorem says the union of an arbitrary collection of open sets is open, and the intersection of a finite collection of open sets is open. So let us consider collections of interval. Say 0, 1, 1, 2, and let's say 10, 11. So you understand now why I'm considering collection, because I'm taking intervals and I'm forming another set. So that's why we are considering collections of open sets, because I can have one single open set, but I'm considering the operation union. So I need some more open sets. and hence I need a collection. So an arbitrary union, sorry, the union of an arbitrary collection of open sets is open, and the finite intersection is open. So why this is true? I mean, what is the definition of an open set? We can consider if epsilon neighborhood for all points such that the epsilon neighborhood is contained in the set. So let's say I have a picture, something like this. This. So consider these sets are open. Now, if I take any elements in this union, so I'm considering, let's say this is A1, this is A2, this is A3, this is A4. So since A1, A2, A3, A4, they are all open. So what do we know is if I consider any elements in the set A1, A2, A3, or A4, I can always construct a epsilon neighborhood such that the neighborhood is contained in the set. So if I take the union A1, A2, A3, and A4, and if I take any elements in the union, let's say X belongs to this union, can I construct a epsilon neighborhood such that the epsilon neighborhood is contained in the union? We can, right? Because this definition, I mean, this expression gives us X belongs to A1 or X belongs to A2 or X belongs to A3 or X belongs to A4, right? Okay, so since these sets A1, A2, A3, and A4, they are all open, and if X is an element of any of these sets, then I can definitely construct a epsilon neighborhood. Let's say X belongs to A1. We know A1 is an open set, right? Hence, we know there exists an epsilon neighborhood which is contained in A1. Hence, arbitrary union is the open set. And why we are considering finite intersection? What is wrong with infinite intersection or any arbitrary intersection? Because arbitrary intersection can give us different results. Maybe we can start with open set, and if we take arbitrary intersection, then maybe we can get a closed set. To see this, let us consider the set 1 over n to 1 over n. So where n belongs to the natural number. And definitely I'm considering the natural number without 0. Okay, so, and if I take the intersection, the infinite intersection n equals to 1 to infinity minus 1 over n, 1 over n, this gives me what? Empty set? Sure. This gives me 0, right? Because 0 is in all these minus 1 over n, 1 over n set. If you start with 1, n equals to 1, then you have minus 1, 1, 0 belongs to this set. If you take n equals to 2, then minus half, comma half. So say this is -1 and this is 1, and you are just, so if this is minus half and this is half, but essentially every set contains the element 0. Hence the intersection is just one element 0. And a singleton is basically a closed set. I mean, there are some other mathematical structure that needs to be considered, but just for this, let us consider a singleton is just a closed set. Yeah. No problem. Just let's say you have a set 1, 2 and another set 100, 101. If you take the union, it is just this set and the union, and the union 100, 101. This is just two disjoint sets. Because what is the definition of an open set? We need to consider every element, and if we can find a neighborhood of that element that is contained in the set, then definitely that is the open set. So let us consider a element in the set 1, 2, which is 1.5. Can you construct a epsilon neighborhood which is contained in this union? Yeah, you can, because 1, 5, if you consider the epsilon neighborhood to be 1,5, around the 1.5 points, and the radius of the neighborhood is something like 0.001 that is contained in this set. And you can separately have elements for this set, for which you can also construct a epsilon neighborhood which is also contained in that.
So it is possible to have these joint open sets.
Yeah. Okay. Okay, so now this is basically the definition we are going to adopt to define topology. So yeah. Okay. Okay. Yeah, I think we can start later in the next session, because I'm going to define topology. Okay. Thank you very much. If you have any questions, please.